Hello and welcome to dSPACE Learning Bits. Electric aircraft technology is taking off across the aerospace industry, but developers are faced with unique challenges when it comes to batteries. My guests today are going to talk more about battery safety and electric aircraft applications. Stefan Walter is Product Manager of Electromobility and Electric Drives at dSPACE, and Soeren Reglitz is Product Manager of Strategic Product Management, also at dSPACE. Hi, Stefan. Hi, Soeren. Welcome to the podcast.
Yeah. Hi, Alicia. Thanks for having us.
It's great to have you both here. To begin our conversation, can you tell me what is the state of the industry with regards to electric aircraft? Soeren, could you answer that question?
Yeah, sure. So first of all, when we are talking about aircraft electrification, we need to distinguish between propulsion and non-propulsion systems. And in the propulsion domain, the industry has made a significant step towards all electric aircraft in the past years. So in comparison to hybrid propulsion concepts, all electric aircraft have fully replaced conventional jet fuel by either batteries or fuel cells as source of energy. However, the energy density of batteries or fuel cells is lower than for kerosene. So this puts some severe limitations on flight range, which is a problem, especially for large commercial aircraft on long-range missions. And this is why new concepts are also targeting hydrogen propulsion for so-called zero-emission aircraft. And in this case, liquid hydrogen with a relatively high energy density is used for combustion with oxygen in a modified gas turbine. So this way, it is also possible to perform long-range flights without carbon emissions. But besides the propulsion domain, electrification also affects other parts of the aircraft, of course. So for example, electric solutions are also replacing hydraulic or mechanical systems. And this enables completely new system designs and helps reducing the overall weight of the aircraft. So in summary, there is a strongly increasing demand for electric energy across all aircraft types. And independent of the used propulsion concept, new aircraft designs include batteries or fuel cells as source of energy.
Soeren, can you talk about the challenges of using batteries in electric aircraft, and in particular with regards to safety?
Sure. So for most new aircraft designs today, lithium-ion batteries are used as source of electrical energy on board aircraft. And this is because lithium-ion batteries offer a good energy density compared to lead-acid batteries, for example. However, there are two major issues with this type of battery when it comes to safety on board aircraft. And this is also reflected by corresponding standards, such as DO 311A, for example. And the first issue is thermal overheating caused by overcharging or internal short circuits, for example. If left unchecked, this could lead to combustion or even explosion of the battery, which needs to be avoided at all costs on board an aircraft, of course. And the second issue is functional failure, for example, due to general degradation of the battery during operation. And this is especially important for batteries on board all-electric aircraft because they are ensuring the energy supply also for safety critical functions. This means that additional safety considerations need to be taken into account to achieve type certification and also later on airworthiness certification. So to master those challenges in all-electric aircraft, the use of battery management systems is essential. But this leads to additional need for testing because we need not only to test the batteries, but also the battery management systems, of course. But only this way, the industry can truly ensure safe operation of lithium-ion batteries on board aircraft.
Stefan, my next question is for you. Why do you need battery management systems for handling lithium-ion batteries, and how do they operate?
Yeah, let me explain. As we see here, lithium-ion batteries consist of several battery cells. The different cells are organized in modules and connected in series to provide the total output voltage of the battery pack. Because of manufacturing tolerances and cell individual aging over the lifetime of the battery, each of the different cells here could have a different electrical behavior and energy storage capacity. And this variation have an impact on the charging and discharging behavior of each cell. And therefore, it has an impact also on the safety of the entire battery. To operate lithium-ion batteries safely, it is mandatory to prevent the individual cells from overcharging, over-discharging, and resulting thermal runaways. Therefore, voltages and temperatures of each individual cell must be continuously monitored and maintained. This is done by so-called cell supervision circuits. The cell supervision circuits measures the temperature and balances the voltage of each cell within one of the cell modules. So for each module in a battery pack, there is a cell supervision circuit, and all cell supervision circuits are connected via a communication protocol to the actual battery management system, the BMS. The BMS collects the information from the different CSCs via the protocol, and besides this, it measures the total battery current, the voltage, and runs the actual algorithms. For example, to calculate the state of charge, the state of health, to supervise the cell supervision controllers, and to control the overarching cell balancing. And last but not least, to execute specific safety routines if it is necessary to do so. We already learned that battery management functionalities are safety critical, and therefore we really need to extensively test them.
How do you test a battery management system, and what solutions does dSPACE offer?
Yeah. First of all, testing a battery management system is quite a challenge. Especially when focusing safety aspects, it is necessary to test the behavior and reaction of the battery management system according to different battery conditions. Such battery conditions could be, for example, divergent aging behavior or any faulty conditions of a single cell. Especially for safety aspects, it is also important to specifically test certain corner cases. To simulate such conditions and even simulate hazardous situations to test those corner cases safely, hardware-in-the-loop testing is an ideal technique. For hardware-in-the-loop testing, HIL testing, we basically distinguish between two kinds of testing methods: signal level testing and voltage level testing. Signal level testing focuses actually on the BMS and its algorithm. The cells and the cell supervision circuits are simulated by a simulation model which runs on the HIL system. The device under test, the BMS, is connected via its specific protocol to the HIL system. And the HIL system simulates via the protocol the communication between the BMS and the virtual cell supervision circuits. Voltage level testing focuses beside the BMS also the cell supervision circuits. So BMS and CSC are the device under test. To satisfy the real cell supervision circuits, the challenge for the HIL system is to emulate the real voltages of each single battery cell with a high precision. Common tests on voltage level are, for example, active and passive cell balancing with real flowing current on real cell voltage level. At dSPACE, we provide a complete toolchain for testing battery management systems on both signal and voltage level. If you're interested to learn more about our offerings, feel free to contact me or my colleague. We are really happy to help you.
Well, this was a great talk. Thank you both for speaking with me today.
Thanks for having us.
Thank you. To learn more about dSPACE solutions for electric aircraft applications, please contact Stefan Walter or Soeren Reglitz.
dSPACE, your partner in simulation and validation.